In this example, we're going to use the parallelogram method to add 4 vectors acting on the head of a jib crane. The red line indicates the force of tension in a cable that connects a winch to the load. FAB, the blue line, indicates the force in the tie, which connects the jib back to a vertical post. And FDA is the force that's transmitted along the jib itself. The scale that we are using is 1 centimeter equals 10 kilonewtons. The force in the cable is 50 kilonewtons, and it does not matter which line that we look at, they would both be the same. So based on our scale, this line must measure 5 centimeters long, and if we check and we measure it, it pans out to be 5 centimeters, and likewise this line should measure 5 centimeters long, and it too measures 5 centimeters. So in the parallelogram method, we're going to add 2 vectors together by shifting them around, as we've seen in our previous videos, to create a parallelogram. The diagonal that connects from the origin to the opposing corner would be the resultant of those 2 forces. So we're going to start by shifting force CD over to the tip of force BC. So I have my line on the edge of my triangle leg, and then I'm using this ruler as a guide, and I slide it over here. When I hit the edge of vector BC, I sketch in a dotted line. And I can make that line as long as I want. And we're going to do the same process over here now. We're going to take this line, BC, and slide it so it crosses over line CD. And I'll use the ruler as a guide. And I stop right here. And you can see that this line is not quite long enough, so I'll just go back and extend it a little bit, because we want to see where the 2 lines cross over each other. Right, so the resultant of vector CD added with vector BC is this line right here. It starts at the origin and it makes it all the way over here to the opposite corner. And that's my resultant. And since I'm adding more than 2 vectors, it's possible I'll have more than one resultant along the way. So this is sort of a temporary resultant, and if I add that resultant with either of these other remaining forces, I'll get a new resultant, and if I add that new resultant to the remaining force, I get the ultimate resultant. Just so we can see it right now, this is measuring 9.4 centimeters long. We need to know that a little later on. Okay, this line here, vector DA, when added with this line here, vector AB, will form another resultant, and that resultant would point up and to the left. And because we're talking about the head of a crane, the net force at that point should be 0, so the resultant caused by these 2 forces would be the equilibrium to this resultant right here. So I'm going to extend a line backwards, like so. And this is the line of action, and the equilibrium ought to be on that line of action. And I happen to know that that equilibrium ought to be 9.4 centimeters long. So I'm going to check here. So that's the spot right there where the equilibrium will be, right here. That's an important spot to note. So an arrow that points from here to here would be equal and opposite to this. They cancel each other out. So I'm going to use this information to determine the proper sizes and the proper strengths of these two forces. I'm going to start with this one right here, the force dA, which is a force in the jib. And what I'm going to do is extend its line of action out here. Force AB, when added to the end of the vector, which is somewhere out here, would end up pointing at this spot right here. So I'm going to use the same technique for sliding vectors that I've used before, and that's what I've got here. Is I've got my straight edge along force AB, and my guide is up here, so I can now start to slide this vector around. When this vector reaches the end of the equilibrium, which is that spot, I stop and I draw a line that connects from force dA's line or action to this point right here. This line, when measured, is force AB. And the line that connects from here to there, when measured, is the force dA. So these are your forces in the jib and the forces in your tie. So we'll stretch that out to there. So I'm going to measure it now because the ruler is already in place. And if we measure carefully from here to here, this is 10 centimeters long. So force dA, which is technically the force in the jib, is 10 centimeters long, and with my scale of 1 centimeter equals 10 kilonewtons, means this is 100 kilonewtons. And if I look at this line up here, it measures 1.8 centimeters. So again, using my scale, that would be equal to 18 kilonewtons. And then the resultant right here, as I said, should measure to be 9.4 centimeters, which would be 94 kilonewtons.